Okay, starting video 4 then on our sequence of videos on neural machine translation. How do we represent words? Well, we use one hot vector. So a one hot vector is a vector which is composed entirely of zeros except for one entry where there is a 1. This distinguishes each word. So each word has a distinct one hot vector. So you can see here that for dog, 1, 2, 3, 4, the fifth position is occupied by a 1 and all other entries are or other positions are occupied by a 0. For cat, it's the looks like the 8th one. For eat, it's the 2nd one, etc., etc. Now, clearly, you know, the little t there is for transpose. I mean, I have things looking horizontally here, but a vector surely is a vertical concept. So you can actually, you know, view these or visualize these, you know, going from top to bottom rather than from left to right. But as I said earlier on, in order to stop the matrices from being too large and then the number of calculations being, you know, completely astronomical, we limit the vocabulary to, let's say, 20K or 30K or 50K or 70K. And then anything which is below that, which is cut off, we just have a token which represents all those other items. And of course, similar words behave similarly. So, you know, you can see here that dog can appear in all of the instances where cat can, because they're very similar words. So we actually, you know, represent words in terms of their word embeddings. So you know, there's a program, you know, which, you know, we all use all the time called Word2Vec, which is a group of models that produce word embeddings, shallow 2-layer neural nets that are trained to reconstruct the linguistic context of words. And Word2Vec takes as input a large corpus of text and produces a vector space of several hundred dimensions with each unique word occupying or assigned a vector in that particular space. And as you can see here, word embeddings positioned in the vector space for particular words that share common context occur very similar positions in that space. So we can see here that the mapping from king to man is exactly the same as woman to queen. So if you look at the first parameter for king and man, it's 45 different. Between woman and queen, it's 45 different. Between the next one, it's 89 difference, 26 difference for the third one, 26 difference for the third one, and 56 for the fourth one. So you can see that king is to man as woman is to or queen is to woman. You can see there that the only difference between, you know, king and queen are that, you know, for the first two instances, there are only 5 positions in the multi-dimensional space, different for king and queen. So these items are occurring in very similar positions in that multi-dimensional space. Here I only have 4D, but it could be much higher dimensionality than that, up to 100 perhaps. So as you can see here, in order to, if you subtract the vector for man from the vector for king and you were to add the vector for woman, you'd have a representation of queen. That's the way in which we're thinking about this. Word embeddings are computed they're computed offline, and we use just a lookup table to look up individual words. So the input now is not just words or vectors; it's a word embedding itself. We don't need to compute values for all the output nodes, just those which the model can actually suggest. So here is an example where you can see, you know, all the articles, the a and some, you know, are very close to each other in some multi-dimensional space. Prepositions are close to each other, verbs are close to each other, nouns are close to each other, and even, you know, sub classifications of different types of nouns are close to one another. And essentially, you know, here's a diagram from Philipp Koehn's book, which gives you the architecture of a feed-forward neural network language model, where the context words are represented as a one hot vector and projected into continuous space as word embeddings using the same weight matrix for all words, and the predicted word is computed as a one hot vector via a hidden layer. And this is useful for clustering and also for backoff if we don't have a particular context that we've seen before. And this is the switch point, where we are going to abandon feed-forward modelers and switch over to recurrent modelers, which condition on any length context sequences. And we'll see that they do this by reusing the hidden layer when predicting a particular word as additional input to predict the previous word. We'll, in trying to predict a particular word, is going to use the last output word that it predicted in order to, so it's got some history in order to try to firm up on the next word that it might predict if we're just predicting an English sentence, or we're trying to predict the English sentence as a translation of an Irish sentence, for example. So feed-forward networks are good at processing inputs and outputs of fixed size, but in order to process sequences of words, it's better to use RNNs, which read one input at each step. The network has layers that are self-connected, and when they process their input, they also read their last output, their history. So if you can see here, the example, we have 1, 2, 3, 4, 5, 6 input words. So we have 6 input nodes represented that, and you can see the recurrence in the neural network where each of the items in the hidden layers are connected with themselves. And we have on the right-hand side the time unfolded representation of the state of the network for when the word the is processed by that network. So you can see the first set of gray nodes is equivalent to the state of the hidden layer at the first hidden layer, and then the second hidden layer, and then the output layer. And here is the time unfolded RNN for the whole sentence, the cat on the mat. So this is equivalent to the RNN. It's just we're not showing all of the connections at the same time.